Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Alpesh Dafda, and in this 24th video class of DIP, we will study different noise models in digital image processing. So what is noise? As we know in electronics and communication engineering, noise is any unwanted signal that gets added in our desired or wanted signal. For digital image processing, noise is any undesired variation in intensity of pixels that gets added to our desired image. So we'll be studying different noise models. Now these noise models are based on different statistical distribution of data, right? So we know that there are different types of noise models, and now the question may come in your mind that why do we need to study these noise models? So the benefit of understanding these noise models is that we can easily identify noise type and apply filters for that to remove the noise. Okay, so let us start. So in the previous video class, we saw this model of image degradation and restoration. And to understand the restoration process, it is important to understand the noise function eta xy or n of u v. So a good restoration technique can be built if we have realistic noise models. The noise in digital image processing are usually additive or multiplicative noise, and we will confine our study to the additive noises only. So this noise is described by its probability characteristics, and through histogram of the image we can visualize the effect of a particular distribution. Okay, so the sources of noise in digital images arise during image acquisition or digitization of the image and or transmission. So during image acquisition, the imaging sensors can be affected by ambient conditions. For example, see, the performance of imaging sensors is affected by a variety of factors such as environmental conditions during image acquisition and by the quality of sensing elements themselves. For example, in acquiring images with a CCD camera, light levels and sensor temperatures are major factors affecting the amount of noise in the resulting image. Also, the interference can be added to an image during transmission. So this happens principally due to interference in the channel used for transmission. For example, an image transmitted using a wireless network may be corrupted as a result of lightning or other atmospheric disturbances. And to understand the restoration process, it is important to understand the noise function. But this noise cannot be predicted. Why? Because it is any unwanted and undesired random variable, but we can approximate it by using statistical way, using the probability density function or PDF, right? Let's go ahead. There are different types of noises, and for digital image processing, we'll be confining our study to 6 different noise models. First one is Gaussian, which is the most common model. Second one is Rayleigh model. Third one is Erlang or gamma distribution. Fourth one is Exponential model. Fifth one is uniform model, and sixth one is impulse or salt and pepper noise model. So very first distribution is the Gaussian noise, which we all know is having a bell-shaped function like this, and this is the mean. The sigma is the standard deviation and sigma square is the variance. So mean means the average value, sigma is the standard deviation, how much it deviates from the mean value, and variance is the total distribution from the mean value. So from this mean value, this is the negative variance and this one is the positive variance. And we know for this Gaussian distribution, the mean and variance are roughly equal on both the sides. And because of its simplicity, this Gaussian noise provides a good model of noise. So if for any digital image we do not know which type of noise it is, we can apply the Gaussian noise distribution model to it and consider that the noise is a Gaussian noise. And that is the reason that they are very popular, and at times when all other noise model fails, Gaussian noise model works for obtaining better output. So this PDF of Gaussian distribution is also known as normal distribution, and Gaussian noise is a random noise that enters the system and it affects both dark and light areas of the image. So it is given by this equation where Z represents the gray level in the image and P of Z is the PDF of this gray level or probability of occurrence of this gray level. Sigma is the standard deviation and mu is the mean, sigma square is the variance. The second noise function is the Rayleigh noise function. So unlike the Gaussian distribution, the Rayleigh distribution is not symmetric, right? As you can see here. So it is different from the Gaussian distribution as this particular portion is same as the Gaussian distribution, but this left portion is a abrupt portion, that is rising abruptly. Here there is smooth variation, whereas this one is straight, right? So unlike the Gaussian distribution, the Rayleigh distribution is not symmetric, and the Rayleigh distribution is skewed to the right side. It is given by this equation, and this type of noise is present in range images, which are used in remote sensing applications where pixel value indicates the distance between the object and the camera. So next distribution is Erlang distribution. As you can see in the figure, the Erlang distribution starts from 0 and doesn't start from some mid value like the Rayleigh value. And the shape of this gamma distribution or Erlang distribution is similar to the Rayleigh distribution, but it starts from 0, and this is the equation of Erlang distribution. And this gamma noise occurs due to illumination problems for digital image processing. The next one is exponential noise. As the name suggests, it is an exponential decaying value like this, and this is the equation for exponential noise, and this one is for. So this exponential noise occurs due to illumination problems, and it is usually seen in laser imaging. Next one is the uniform noise. So as the name suggests, this noise is uniform over a certain band of gray levels. As you can see here, the PDF of uniform noise is given by this equation. And for this uniform noise, different values of noise are equally probable, and it occurs due to image quantization error. Last one is the impulse noise, which is also known as salt and pepper noise. So this we have already discussed in image enhancement in the spatial domain. It is given by this equation, and it occurs mostly due to sensor and memory errors, because of which pixels gets false maximum values. Now how this equation comes, let us understand. For Gaussian noise, this is the mean value of the Gaussian curve, this is the negative standard deviation, and this is the positive standard deviation, and this one, this total is the positive variance, and this one is the negative variance. So if you see that this value is equal to this value for Gaussian distribution. So if you put the values of z in this equation, you will get such type of bell-shaped curve. So for the Gaussian distribution, 70% of the value is in between mu minus sigma to mu plus sigma, and 90% of values comes in between mu minus 2 sigma to mu plus 2 sigma. So this gives you 90% of the values of this distribution, and only 10% is here and here. Okay. So similarly, you can get the distribution for different noise models. Now let us understand these different noises using examples. So if this is a test image or test pattern for demonstrating the noise models, then this is the histogram of this test pattern. Through histogram of the image, we can visualize the effect of particular distribution. So we know what is histogram. Histogram is the frequency of distribution of different gray levels. So say this gray levels are ranging from 0 to 255. So 255 is white, 0 is black. So this white circle is having this levels of distribution, this gray is having this levels of distribution, whereas this black is having this levels of distribution. Now the next slides will show the result of adding noise based on various models to this image, and we will see how this distribution gets affected, right? So when the Gaussian noise is added to the image, you can see the histogram variation for the Gaussian noise. Okay, so you can see the bell-shaped curve clearly over here, right? Similarly, you can see the Rayleigh curve over here skewed towards the right side. You can see the Erlang noise, gamma noise from such distribution in the histogram. Similarly, you can see the exponential noise gives the exponential pattern, the uniform noise gives uniform pattern, and the salt and pepper noise or impulse noise gives different impulses in the histogram like this. And this is of course how the image looks when impulse noise is added, uniform noise is added, exponential noise is added, as well as the Gaussian, Rayleigh and Erlang noise or gamma noise gets added to the image. Okay, I hope it is clear. The advantage of studying these noise models is that if we take the image and form the histogram of that image, then using the histogram we can directly judge that this particular form of noise has get added to the image, and hence now we will design our filters in such a manner that this particular noise gets removed. So that is all for this video class. I hope you would have gained a good knowledge from this video class. Thank you very much.